Hello, my name's Darren and welcome to the Maker's Rage podcast. So this is a re-edit and re-recording of an earlier episode I did on thought experiments, which I was never really happy with. I've earmarked 2 other episodes for similar treatment, the one on the epic muse Calliope and its companion episode on the hero's journey. As for new material, another one on the muses of course is upcoming, and I'll be starting a new series on revolutions, with episodes dedicated to political revolutions, scientific ones, revolutions in philosophy, in culture and the arts, etc. Anyway, with that preamble out of the way, here's the updated version of thought experiments. When Einstein was 16 years old, so around 1895 or 1896, he appears to have conducted his first ever thought experiment, and a simple one on the face of it. He imagined what things would look like if he was riding on a beam of light. At the time, he conjectured, as most 19th century theorists would have done, that light doesn't travel in a vacuum, but like sound, requires a medium to transmit it. And sound travels in a variety of media, like water and air, hence the tagline from the 1979 movie Alien, "In space no one can hear you scream." But unlike sound, light does transmit in space, but it wasn't obvious what medium carried it. It was clearly something less tangible, detectable than air and water, and physicists imagined something more ethereal, and indeed they called it the ether. And then they set about trying to detect it. Spoiler alert, they failed. As for Einstein's thought experiment, which didn't depend upon the existence of the ether, he imagined himself riding on a beam of light and asked himself, what would the beam look like when he was travelling at the speed of light? Lord Kelvin, 19th century stalwart of classical Newtonian physics, might have demurred at Einstein exercising his imagination thus, and advised him that it's best not to develop any grand designs on making notable contributions to theoretical physics. He and his contemporaries had worked everything out. All that was left to do was dot the I's and cross the T's. As for space and time, they are absolute. Light transmits in waves. Gravity is what Isaac Newton said it was. God is in his heaven, and all is right with the world. Of course, great that he was, Kelvin was an old fogey. He probably wasn't even aware that in 1887 the American Albert Michelson, along with his colleague Edward Morley, proved there was no ether, that light travels at constant speed in a vacuum, paving the way for the special theory of relativity 20 years later. Of course, Einstein himself didn't know this when he was riding a light beam at 16. And if it was ever mentioned at school, he likely wasn't paying attention. With 50 years of hindsight, he recollected the fledgling thought experiment thus, quote, "A paradox upon which I had already hit at the age of 16. If I pursue a beam of light with velocity c, the velocity of light in a vacuum, I should observe such a beam of light as an electromagnetic field at rest, thus spatially oscillating. There seems to be no such thing, however, neither on the basis of experience, nor according to Maxwell's equations. From the very beginning it appeared to me intuitively clear that judged from the standpoint of such an observer, everything would have to happen according to the same laws as for an observer who relative to the earth was at rest. For how should a first observer know or be able to determine that he is in a state of fast uniform motion? One sees in this paradox the germ of the special theory of relativity is already contained. Well, as they say, hindsight is 20/20, given the impression that he intuited the special theory of relativity at 16, before he knew anything about the constancy of the speed of light as a cosmic limit, before he learned Maxwell's equations, which he wouldn't learn until 1898, 2 or 3 years after his thought experiment reputedly happened. He also claimed that the idea for general relativity came to him when he saw a painter falling off a ladder. Ronald W. Clark, in his definitive biography of Einstein, said that accounts like these are typical of what Einstein's eldest son called his delight in making up good stories, and he was certainly an example of a great scientist who was also a great science communicator. But does it really matter if he was as precocious as the light beam anecdote seems to indicate? At 25 he wrote the great paper that sealed his immortal fame on the electrodynamics of moving bodies, which introduced the world to the special theory of relativity. The 81-year-old Lord Kelvin had 2 years left to live, and if he read the paper at all, I doubt he realised its implications. But relativity would be contentious, and would remain so even by 1921, when Einstein was awarded the Nobel Prize, and not for relativity. Instead, the citation reads that he won it for, quote, his services to theoretical physics, and especially for his discovery of the law of the photoelectric effect. The photoelectric effect being just one of the papers he published in that year of wonders, 1905. As for his very first thought experiment, he didn't have a degree, nor the training in advanced mathematics, no familiarity with the latest breakthroughs in theoretical or experimental physics, just his imagination, which he would later say is more important than knowledge, because unlike imagination, knowledge is limited. But once he became the grand panjandrum of physics and science in the 20th century, he'd continue to use thought experiments to illustrate and reinforce his ideas, especially in dialogue with his colleagues and rivals, asking them to imagine scenarios that could be feasibly created according to physical laws, experiments that could be feasibly set up if the technology was available, or the funding. The only limit that must be agreed upon, the only constraints or rules that are required to play this game, and the thought experiment is a kind of game, is that the known laws of physics must be obeyed. This is what distinguishes a thought experiment from a flight of fancy, and the best thought experiments can be apprehended by any lay member of the public, or a 16-year-old who has yet to learn the physical laws and the mathematics that must bridle or discipline his boundless imagination. In his popular work, Relativity, the Special and General Theory, Einstein translates the formal presentation of these theories into a thought experiment involving a train, a railway embankment, and flashes of light. I still remember the first time I saw this explained by Jacob Bronowski, when as a teenager in the 90s I used to stay up late, until the early hours of the morning actually, waiting for the BBC Learning Zone to start, and Jacob Bronowski's The Ascent of Man. In the episode entitled The Majestic Clockwork, Bronowski climbs aboard a tram in the city of Bern in Switzerland, where Einstein had his Annus Mirabilis, or Year of Wonders, in 1905, writing the 5 papers that, had he written nothing else thereafter, would have secured his reputation as among the greatest physicists the world has seen. And to illustrate the puzzling features of one of those papers, on the electrodynamics of moving bodies, Bronowski wants to speed this rickety tram up to approach the speed of light, and using somewhat crude and yet charming 1970 special effects, the tram speeds up and starts getting squashed horizontally, illustrating, as the special theory predicts, that as an object approaches the speed of light, its length contracts in the direction of motion. And likewise for the passenger in the tram looking out the window, the buildings seem to get squashed together, although significantly enough their heights remain the same. But if the passenger then turns and looks ahead, the tops of the buildings seem to bend inwards and forward towards him, forming a kind of tunnel. And of course, people and cars are distorted in a similar way. You can imagine how the old Newtonians would have reacted to this news. One of the implications of the speed of light being a cosmic limit is that not only can nothing go faster than the speed of light, but no matter the velocity of a person in the tram, say, or in a spaceship, they will measure the same speed of light as someone back home on Earth, standing still, waiting on a tram. In other words, light has the same speed in all reference frames. 300,000 kilometers per second, whether you're sitting on a couch with a bag of chips, or trundling along on a rickety tram, or blitzing through space aboard the Millennium Falcon. Newton and his contemporaries didn't think light had a measurable velocity at all, but that it moves from one point to another instantaneously, which is why Newton believed space was absolute and time. Einstein showed neither was the case, that on the contrary, space contracts, and time, well, what does time do? It dilates. Time moves more slowly as it gets closer to the speed of light. And the person in the tram, moreover, ages more slowly than you do. Now remember when I said earlier that the person on the tram, let's say it's Bronowski himself, notices that the buildings get squashed and the cars and the people on the platform, the way the people on the platform see the tram getting squashed. Does the time dilation effect therefore not cancel out? The answer is no, which is why engineers factory set satellite clocks to tick slower to compensate for the fact that the clocks on GPS satellites, for example, run faster by about 38 microseconds daily. One of Einstein's friends, Paul Langevin, proposed another famous thought experiment to illustrate this quote-unquote paradox. Langevin is an interesting character. One of his doctoral students was Pierre Curie, Marie's husband, who died prematurely after getting run over by a horsing carriage. Langevin would go on to have an affair with the widowed Marie, and this would cause a bit of a scandal. Marie's daughter by Pierre, Irene Joliot Curie, would become another of Langevin's doctoral students, and, like her mother, go on to win the Nobel Prize in Chemistry. Incidentally, Langevin is seated next to Einstein in the famous 1927 Solvay Congress photo that features pretty much all the Avengers of mathematical physics of the time. It's one of the most extraordinary gathering of minds in history. To Einstein's right is Hendrik Lorentz, whose transformations implied that length contraction and time dilation happen to be a consequence of the speed of light being constant. And to his right is Marie Curie herself, the only woman in the photo and the only person with 2 Nobel Prizes. There were 29 attendees in total. 17 would go on to win the Nobel Prize. Among them were other members of the old guard like Max Planck, seated next to Curie, on whose work younger arrivistes like Max Born, Erwin Schrödinger and Niels Bohr were developing the theory of the quantum. And representing the future, Heisenberg, Dirac, Pauli. What a headache these would cause Einstein in the coming years. But we'll get to these. First, back to time dilation and Langevin's famous thought experiment involving identical twins. We're asked to imagine one of them, Dan say, staying on Earth while his twin brother, Han, climbs aboard the Millennium Falcon and travels to Alpha Centauri or some other not too distant star, stays long enough to drop a probe or something that makes the return voyage. According to Einstein, when only a few years will have elapsed for Han, when he gets back to Earth, he discovers centuries have gone by, and that his twin brother, the nieces and nephews he never met, etc., are long dead and buried. Langevin called this the twin paradox, because if, according to Einstein, space and time are relative, can't we imagine the Millennium Falcon standing still in space and the Earth zipping away from it at 99% the speed of light? The point to remember here is that this only applies if we cannot determine who is moving and who is stationary. Like when you're on a train and you're not sure whether you're the one moving or the train opposite. Since we were able to set things up so that we knew that Dan back on Earth was stationary and Han was the one moving in the spaceship, special relativity predicts that time dilation only occurs for the moving object. Because being stationary, Dan doesn't cross reference frames. As the moving observer, Han exists in both the stationary and the moving reference frames, and as a result ages more slowly relative to Dan. If some of that went over your head, don't worry about it. None of this is easy to explain without the maths, and even with the maths it's difficult to wrap your head around. And when I was 14 and stayed up until 2 a.m. to watch Jacob Bronowski explain it in The Ascent of Man, I can't pretend I understood it all, but I was, to quote Hamlet, wonder wounded, the kind of wound which afflicts you with the desire to learn more. 7 years after The Ascent of Man first premiered in 1973, in another acclaimed 13-part series directed by Adrian Malone, Cosmos, A Personal Voyage, Carl Sagan tries to explain the very same phenomenon, this time using a bicycle in Tuscany. But I always preferred Bronowski's version, probably because I encountered it first, and I always had a soft spot for that peculiar plummy delivery and that rolling rhoticism that was perhaps a remnant of the Polish accent he tried to shake off early in life. He stood barely 5 feet tall and spoke with a calm assurance of his calling, and a confidence in the breadth of his learning in both science and the arts, which never gave the impression of pedantry, but always of his humanity and enthusiasm to impart without condescension all the wisdom he'd accrued. And having lived through both world wars and travelled to Hiroshima to see the after effects and destruction wrought upon that city by the bomb, a tragic consequence of the advances made by scientists in the 20th century, by many of the people in that famous Soviet Congress photo I referenced earlier, including Einstein, Bronowski knew it was important for scientists like him, for public intellectuals, to remind us that science may produce much that is good, but it is, after all, a human activity, and scientists are human beings who occasionally forget the power they wield, the power they confer onto the world for others to wield, for good or bad. But crucially, science itself is neither good or bad. Gravity isn't there to make us wicked. Length contraction or time dilation doesn't care about our politics, or the speed of light or sexual habits. It is human beings who decide to make a transistor or a bomb. He died at 66 of a heart attack in 1974 in a New York taxicab, just after The Ascent of Man was released. He didn't have long to enjoy the fruits of his labour. Still, it's there in all its glory on the internet for anyone who's interested. Of course, both Bronowski and Sagan are examples of truly great science communicators. They may not be as famous for the contributions they made to their respective fields of study, but between them inspired millions, I'm sure, wonder wounded like me, to want to learn more. And the great thing about television is thought experiments can be brought to life, even if with crude 1970 special effects. The twin paradox and the speeding tram thought experiments are perhaps the most famous in special relativity. For Einstein's general theory of relativity, which includes gravity, Einstein asks us to imagine being in a windowless elevator. You could be standing in an elevator that's stuck in a building on Earth, and you feel the force of the Earth's gravity against your feet. Or you could be in an elevator aboard a spaceship, accelerating in space, at the same rate as the acceleration due to gravity on Earth. The principle of equivalence states that not only can you not tell the difference, unless you had a window and could look outside, but there's no way to measure the difference between these two effects. In other words, the effects of gravity and acceleration are locally identical, suggesting gravity isn't a force, but a curvature of space-time. And when it was proved in 1919 that light from a distant star would curve around the sun during an eclipse, Einstein became the first theoretical physicist to become a worldwide celebrity. But his most ingenious thought experiments are yet to come, and they didn't involve space-time or gravity, but the quantum. Quantum mechanics is the most successful and accurate theory in the history of science. It explains pretty much everything in particle physics and chemistry, and its predictive power is unmatched. But it has some troubling implications, which were noted early on. The famous double slit experiment is illustrative, and although not a thought experiment, it does resemble one in the simplicity of its setup. Thomas Young, perhaps during a break from trying to decipher the Rosetta Stone, was the first to conduct this experiment in in order to investigate the behavior of light waves. The apparatus consists of a light source, a screen with two parallel slits, and a viewing screen. Such a simple setup, and yet it's capable of demonstrating that light doesn't just behave like waves, but like particles. The debate isn't a new one. Isaac Newton thought that light consisted of particles or corpuscles. One of his contemporaries, Christian Huygens, believed they were waves. It wasn't until 1897 that J.J. Thomson discovered the electron and tentatively proved Newton correct. His son, George Paget Thomson, proved that these very electrons, these particles, diffracted like waves, proving Huygens correct. The fact is, the double-slit experiment demonstrates both were correct, and that both Nobel Prizes were deserved. The idea that a particle can be fired through a slit, and then it diffracts like light, is weird. Imagine you're firing a machine gun at a bulletproof screen, and only two slits for bullets to pass through and strike the opposite wall. After firing enough bullets to ensure enough get through, what pattern would you expect to see on that wall? Two vertical strips of bullet holes, of course. Now instead of bullets, try firing photons. If they are indeed like particles, what do you expect to see? Well, two strips of light where the photons struck the screen. So you look at the screen and what do you see? Not two strips, but a series of them. Light and dark, growing fainter the farther away from the centre of the screen you go. An interference pattern that we get with waves. It wouldn't have troubled Thomas Young, who believed light transmitted in waves. But after the discovery of the electron, and that moreover this particle diffracts like a wave, this was the first indication of what would later be termed quantum weirdness or quantum strangeness. They even tried doing the experiment by firing photons one at a time. Imagine firing a handgun at a screen, one bullet at a time. You could wait an hour in between shots, even days, as long as you want. Well, they did this with photons, and still the diffraction pattern was produced. And moreover, when they covered up one of the slits, they got the expected pattern, a single strip of light. But once they uncovered the other slit again, the interference pattern returned. And it doesn't matter if you wait an hour or a year or a millennium between each photon firing, it will always produce that same pattern. It's as if the photon is a particle when we're looking at it and a wave when we're not, or a particle when we fire it and when it lands, and a wave on the journey between the light source and the screen. The idea that a photon or electron or any other elementary constituent of matter could behave both as a particle and a wave still disturbs anyone today who tries to wrap their head around it. 100 years ago, when physicists were still coming to terms with the implications of the new quantum theory, it was clear a new interpretation of reality was needed. The first to propose such an interpretation were Niels Bohr and Werner Heisenberg, mentioned earlier. It would be called the Copenhagen interpretation of quantum mechanics, after the city in which the two physicists did their greatest work in the 1920s. To put it bluntly, we must simply accept that there's a veil between us and the quantum world, behind which there is no solid reality, as we understand it. Only by looking, by peeking through the veil, does it adopt a semblance of reality. But until we look, there is only a fuzzy soup of potentialities, possibilities, probabilities. The photon is a wave until we measure it, until we look and see where it struck the screen. As a particle, the act of measuring, in a sense, makes it real. Like slamming one's hand down on a spinning coin makes it definitively heads or tails. And it was the probabilistic aspect of the interpretation that Einstein never really came to terms with. He does not play dice, he once said to Bohr, referring to God, and perhaps thinking of the double-slit experiment and the idea that nature is somehow playing a trick on us. He said elsewhere, God may be subtle, but he's not malicious. At last, an exasperated Bohr insisted he stop telling God what to do. And just to clarify, Einstein's God wasn't Allah or Yahweh, the old bearded man in the clouds. He believed more in Spinoza's God as cosmos, order, harmony. God is everything, and everything is God, said Spinoza. The cosmos is all that is, or ever was, or ever will be, said Carl Sagan. Anyway, despite Einstein's misgivings, it was at the Solvay Congress in 1927, which I keep referencing, that Max Born and Werner Heisenberg declared, quote, "We consider quantum mechanics to be a closed theory, whose fundamental physical and mathematical assumptions are no longer susceptible of any modification." Let's just say Einstein didn't agree. Anyway, what seemingly happened next was a kind of intellectual jousting. Although Einstein threw down the gauntlet even before the Congress began, saying in a letter to Max Born, "Quantum mechanics is very impressive, but an inner voice tells me that it's not yet the real thing. The theory produced is a good deal, but it hardly brings us closer to the secret of the old one." I suppose this is what Stephen Hawking would later deem the mind of God. During the Congress itself, it soon became clear it would be the great Dane Niels Bohr who would step up to the plate. And Einstein was in the minority, since most present at the conference agreed, at least in principle, with the Copenhagen interpretation. The debates began as dining room discussions, where Einstein challenged Bohr and his supporters on the assertion that quantum mechanics in its present form can be called complete. He also didn't like Heisenberg's uncertainty principle, which states that you can't know simultaneously both where a particle is and where it's going with arbitrary precision. The better you know one, the less well you know the other. And this is inescapable. It's actually a law of nature. And a new one at that, apparently, proposed a couple of years earlier by the 25-year-old Heisenberg. Of course, Einstein's challenges came in the form of increasingly clever thought experiments intended to prove that position and momentum could in principle be simultaneously known to arbitrary precision. For example, one thought experiment involved sending a beam of electrons through a shuttered screen and recording their positions as they struck a photographic screen. Sounds a little like the double slit experiment. Anyway, Bohr and his allies would go away and think about it, and return usually by the end of the day with an adequate counter thought experiment. On the last day of the conference, Einstein voiced his objection to another aspect of the Copenhagen interpretation that bothered him, one that appeared to allow action at a distance, or the ability for two objects separated by a great distance to communicate at speeds greater than light. This would violate the principle of relativity, the theory for which he's most famous, and on which his reputation as the Newton of the 20th century rested. And he would continue working to challenge this feature of quantum mechanics in particular over the next several years, and he never really came to terms with it, right up until the end of his life. And despite being front and centre in that famous Solvay Congress photo, the consensus was that Einstein had lost the debate, and even his closest allies during the conference, for example, Prince Louis de Broglie, whom Wolfgang Pauli seems to be looking at with disdain in the photo, conceded that quantum mechanics appeared to be complete. Of course, Einstein wasn't going to give up that easily, so a couple of years later, at the 6th Solvay Congress, this time the topic was on magnetism, in 1930, he came armed with a new thought experiment. He described a box full of light and suggested that both the energy of a single photon and the time it was emitted could be determined precisely. This would violate Heisenberg's uncertainty principle, since time and energy, like position and momentum mentioned earlier, are, according to the Copenhagen interpretation of quantum mechanics, variables governed by uncertainty. In the thought experiment, Einstein says, first, the box can be weighed, after which a single photon can be released at a particular instant to a shutter operated by a clockwork inside the box. After this, the box can be weighed again, at which point we know the change in its mass, and thus the energy of the photon can be calculated from, you guessed it, E equals mc squared. The energy change would then be known, as would the precise time when the photon was emitted. So that's the end of your uncertainty principle. You can imagine Bohr and Heisenberg wincing at Einstein using his famous equation like a sledgehammer. And his jousting partner, Bohr, was indeed stumped initially. He reputedly stayed up all night, not thinking about magnetism, which is what the Sixth Solvay Congress was supposed to be about, but trying to find a flaw in Einstein's formidable thought experiment and rescue the Copenhagen interpretation. The following morning, he showed up with a drawing of Einstein's box of light and offered the following refutation. When the photon is released, there will be a recoil, causing an uncertainty in the position of the clock and the Earth's gravitational field. This will produce a corresponding uncertainty in the time recorded, due to, believe it or not, Einstein's own general theory of relativity. Einstein had brilliantly invoked his own special theory of relativity to refute quantum uncertainty. Bohr had rebuffed his challenge by invoking Einstein's general theory of relativity. An extraordinary intellectual duel, which on this occasion ended in victory for Bohr, who in retrospect had the advantage of being correct. As I said earlier, quantum mechanics today is the most successful theory in the history of physics. Some would go further and say it is the most accurate, successful, and brilliant theory ever conceived by human thought. For example, in quantum electrodynamics, it correctly predicts the magnetic moment of the electron to an accuracy of about 1 part in a trillion. No other theory in science predicts anything that is then later confirmed by experiment with that kind of precision. 100 years ago, though, the people who developed it, including Einstein, were still relatively young, and there were still many experiments to be done. And by the 1930s, despite apparently losing the uncertainty battle, Einstein wasn't done challenging the implications of the Copenhagen interpretation, and the one that troubled him more than uncertainty, non-locality. It would take him 5 years to produce his next challenge, though. 5 years during which the quantum theory had achieved more or less general acceptance in the physics community, and despite its troubling implications, which even its most ardent defenders had to agree were unsettling, no one could ignore its success in the lab, where time and again experiments vindicated the results of theoretical predictions. And between 1930 and 35, politics, history was beginning to intrude. Hitler had risen to power, and European physicists who congregated in places like Göttingen, where Max Born and Wolfgang Pauli were based, Berlin, where Einstein was teaching, and of course Copenhagen, where Bohr, Heisenberg and Dirac were denizens, cities not that far apart, and from which all could congregate in a place like Solvay in Belgium. It became clear by the mid-1930s this would no longer be possible with the direction Europe was going in. And whereas before Einstein benefited from close contact with these compeers, now he was languishing in the idyllic setting of the Institute of Advanced Studies in Princeton. Nevertheless, it was here that he collaborated with two younger colleagues, Boris Podolsky and Nathan Rosen, on a paper whose title echoed what Max Born had said 8 years previously at the Fifth Solvay Congress. That is, that quantum mechanics was closed and complete. The title of the Einstein-Podolsky-Rosen paper, or EPR, as it became known, was Can a Quantum Mechanical Description of Physical Reality be Considered Complete? Electrons only have a handful of properties, and one of them happens to be spin. An electron can have spin up or spin down, and we can detect this. In fact, it's possible to obtain a pair of electrons in a so-called singlet state, where their spins cancel to give a total spin of 0. Consider such a singlet state, and let's call the two electrons A and B. Now let's say the spin of A is measured and found to be in the up state. Because the two spins must cancel to 0, it follows that electron B must have spin down. Before the quantum revolution, one might have drawing a comparison here with a pair of gloves. You put the left glove in one box, the right glove in another, and move them wide apart, even light years apart. If you open one and discover the left glove, you immediately know the one near Proxima Centauri is the right one. So what's the problem? To illustrate what the problem really is, I will cite perhaps the most famous thought experiment of physics, Schrödinger's cat. Erwin Schrödinger was one of the handful of people in that Solvay Congress photo who was, with Einstein, dissatisfied with the Copenhagen interpretation, and would in fact later repudiate his involvement in the quantum revolution, despite having contributed as much as anyone. You see, he believed that phenomena like wave-particle duality weren't intrinsic to the particles, but a reflection of our incomplete knowledge of them. By looking, we determine where the particle landed on the screen in the double-slit experiment, say. By opening the box, we determine whether the glove is the left or the right one. Max Born, who, if you remember, annoyed Einstein by saying quantum theory was complete, stated that Schrödinger's own wave equation determined only the likelihood or probability that an electron, say, will be found in a certain position, and that moreover, this is not probability due to ignorance, as Schrödinger would have maintained. This probability is all we can ever know about an atomic system, because it is the reality of the system, despite what we can and cannot know about it. Well, Schrödinger wasn't having it, so he came up with his own thought experiment. Imagine, he says, an experiment in which a live cat is placed in a box with a radioactive source, a Geiger counter, a hammer, and a sealed glass flask containing deadly poisonous fumes. When a radioactive decay takes place, the counter triggers a device releasing the hammer, which falls and breaks the flask. The fumes will then kill the cat. And now suppose the radioactive source is such that quantum theory predicts a 50% probability of one decay particle each hour. After an hour has passed, there's an equal probability of either state, the live cat or the dead cat state. Quantum theory, according to Max Born, would predict that exactly 1 hour after the experiment began, the box would contain a cat that is neither wholly alive nor wholly dead, but a mixture of the two states, or a superposition of two wave functions. And this is intrinsic to the system because quantum probability is not based on the ignorance of the observer. If this sounds a little ridiculous, Schrödinger intended it to be. The idea of a cat in a box that's both dead and alive is clearly absurd. Max Born wasn't laughing though. His response was something along the lines of, exactly. We have a superposition of states that is intrinsic to the system. As soon as we, as the observers, lift up the lid of the box to find out if the quantum prediction is correct, the impasse is resolved. The act of observing collapses the superposition of the two wave functions to a single one, making the cat definitively dead or alive. And if Schrödinger had cause to be turning in his grave, it would be to know that this famous thought experiment, or so-called paradox, is used to teach the concepts of quantum probability and the superposition of states at universities to this day. Now, if this is your first exposure to quantum superposition and you find it hard to believe that Schrödinger was actually wrong and Max Born correct, that the system must be interpreted as one in which a box contains a cat that is both dead and alive, or more precisely, a system that contains a superposition of these two states, you haven't been alone these 100 years. But I'm going to ask you to suspend your disbelief for a little while as we return to the EPR paradox. So we have two electrons, one would spin up and the other spin down in a singlet state, i.e. created in the same event, so that our total spins cancel to zero, and we imagine they're moving apart at close to the speed of light. And once they're sufficiently far apart that it would take some time for light to travel from one to the other, it doesn't have to be as far as Proxima Centauri, it can be light minutes, like the distance from the Earth to the Sun. In the EPR paper, Einstein contended that the spin up was like the right glove, say, hidden in a box, although he didn't use this analogy, And as soon as we open one box and determine what glove is there, we instantly know what the other glove is, and that no information need travel faster than the speed of light. There is no superposition of states. The glove is either left or right from the start. Similarly, the electron spin is either up or down. Opening the box or checking the spin doesn't change this. If there is a superposition of states, however, then we have a big problem. Because then there is no left glove in one box and right glove in the other from the start, but a superposition of the two in each. And only by opening one of the boxes does the wave function or superposition collapse to left or right glove, up or down spin. And by opening one box and collapsing that wave function, the wave function in the other box instantly collapses. So our interfering with one box directly affects the other, and notably this effect is instantaneous. It is spooky action at a distance, and what's worse, being instantaneous, action that transmits faster than the speed of light. Let me just say, we're not in fact sure if it's instantaneous. It's definitely faster than light, but physicists today are still trying to measure exactly how fast it is, or if indeed it is instantaneous. Anyway, another analogy would be a spinning coin that is neither definitively heads or tails. By slamming our hand down on one and seeing it as heads, imagine its spinning pair way off in the distance, light years away, and another spooky hand telekinetically slamming down and determining that it is tails. This is very different to a coin that's heads from the start and the other tails. Anyway, the reason I've belaboured this EPR explanation is because it has remained among the 2 or 3 most troubling aspects of quantum reality, even decades after Einstein's and Bohr's death. And I think it's fair to say Bohr had no adequate response to Einstein's last great challenge. But the physics world had by then accepted that quantum mechanics is correct, despite its weirdness, and I think Bohr had grown weary of defending it. His response in the end was more a metaphysical apologia, exhorting Einstein and other skeptics to simply accept that our hominin minds, which evolved in the savannah, is simply not equipped to understand the world at the level of the quantum. We should consider ourselves lucky we have the insight we do. It's best to just draw a veil on what we cannot grasp. It's best to simply shut up and calculate, in other words. And this became the general attitude towards quantum mechanics for the next few decades. Don't get bogged down in the philosophy. We measure a theory's success by the accuracy of its predictions, and quantum mechanics is the most successful theory in physics. Even Richard Feynman, another quantum pioneer, who developed the path integral formulation of quantum mechanics, and was a major contributor to the theory of quantum electrodynamics, which he called the jewel of physics, for its extremely accurate predictions. Even he discouraged students from getting too bogged down by the metaphysics of the quantum. And he was right in a way. The Copenhagen interpretation, or Einstein's EPR paper, didn't impinge very much on the development of lasers, the transistor, the microchip, the electron microscope, MRI, or GPS. Even the developers of modern computing and the internet weren't thinking very much about the Copenhagen interpretation while making these breakthroughs. But I suppose we should be glad to have those personalities who are never content to accept on fate the counterintuitive, what they can't make sense of fundamentally or adequately explain despite whatever accurate predictions. Those who won't concede to the notion that simply because we evolved from Homo erectus, that we'll never understand what happens at the singularity of a black hole, or why electrons behave the way they do. The telescope and the microscope were both only invented about 400 years ago. Look at what we've discovered since. Should we really simply accept that the universe, of which we are a part, and which has already disclosed so much to us, will keep some secrets to itself? Einstein would have agreed with Spinoza that human beings thinking about nature is natura naturans, or nature naturing, In other words, we small beings thinking about the natural world is in a way nature reflecting upon itself. We may very well be the only beings in the universe who can think, but we are still stardust, a concourse of atoms become conscious, self-aware, and which moreover can reason. When Einstein referred to God or the Old One, he meant the universe and its laws. And on our little planet in the suburbs of a single galaxy, and I'd like to think on other planets in other galaxies as well, the universe woke up and through our ape species began to think about itself. God is subtle but not malicious. The universe may perform a few card tricks, but it doesn't play dice. And so the EPR paper was put in a drawer and not spoken about until 10 years after Einstein's death. John Bell, the Irish physicist, who while on academic leave in 1964 took up the challenge of once and for all settling the dispute. He wrote a remarkably short paper entitled On the Einstein-Podolsky-Rosen Paradox, and in it, amazingly, provided a way for experimentalists to test if Einstein or Bohr was correct. It took a further 8 years in 1972 for someone to take up the gauntlet. That person was John Clauser at the University of California, Berkeley. Initially, he wanted to prove Einstein was correct, that there is no spooky action at a distance, that entangled states exhibit such weird behavior because we have incomplete knowledge of them, that there are, in other words, hidden variables we've yet to uncover. And when we do, we'll have a more thorough understanding of what's going on in the box with a dead and or alive cat. Clauser's thesis advisor discouraged this, of course, as did the great Richard Feynman, who said the work was, quote, totally silly, you're wasting everybody's time and money. But after receiving John Bell's blessing to pursue the idea, he collaborated with Stuart Friedman on an experiment that focused the laser on calcium atoms, making it emit particles of entangled photon pairs that shoot off in opposite directions, and he used filters set to measure whether they were correlated. After hundreds of thousands of runs, they found the pairs in fact correlated more than Einstein would have predicted, proving the reality of spooky action at a distance with hard data. Perhaps because the young Clauser began the project hoping to prove Einstein correct, made some of the old guard a little nervous, and even though this major experiment indicated the Copenhagen interpretation was indeed correct, he wasn't exactly commended for his efforts. I think Einstein's EPR skeleton in the closet made physicists feel uneasy, including the magnanimous Richard Feynman, who threw Clauser out of his office at one point. This suggests to me he knew quantum mechanics rested on shaky foundations, and perhaps he was nervous that this young Turk would, in proving Einstein correct, bring needless controversy to the field he did so much to develop. Well, in the end, Clauser didn't get what he wanted, but the data spoke for itself. Between 1980 and 82, Alain Aspect in France resolved to conduct an even more decisive experiment, one that would prove once and for all that despite his ingenious objections to quantum weirdness, Einstein was definitively wrong. The results were unambiguous. Not only was quantum physics non-local, as Einstein feared, but Aspect's experiment confirmed this in the exact way predicted by quantum mechanics with a statistical agreement of up to 240 standard deviations. Given the technical quality of the experiment and the near-perfect statistical agreement, this is what convinced the scientific community at last. And the numerous experiments performed since the 80s only further confirmed this, which is why Clauser and Aspect won the Nobel Prize in Physics in 2022. The third recipient was Anton Zeilinger of Austria, whose experiments not only reinforced and expanded on the work of Clauser, Aspect and Bell, but would pave the way for quantum computing, quantum networks and quantum encrypted communication. Had he lived, I'm sure John Bell would have won the Nobel Prize outright. He'd already been nominated shortly before his death in 1990, at the age of 62. Bohr was 37 when he won it, Einstein 42. And many of those who were seated in that famous Solvay Congress photo I keep referencing were also in their 30s and 40s and 50s when given the accolade, with Curie living long enough to get it twice, despite being taken away prematurely at 66 from leukemia, likely caused by her exposure to a radioactive element she discovered. But since then, it seems the Nobel Committee has gotten in the habit of waiting until potential laureates have gotten too old to enjoy the accolade, like waiting until they've exited the stage to start applauding, or in Bell's case, exited the building. But if he is out there somewhere in the continuum, refereeing an ongoing duel between Einstein and Bohr, I'm sure, despite the judges having finally called the contest in Bohr's favour, neither of them would be happy with Bell's final assessment. Quote, Bohr was consistent, unclear, willfully obscure, and right. Einstein was consistent, clear, down to earth, and wrong. And I'm sure after graciously accepting the results of Clauser's and Aspey's experiment, and noting that their Nobel was deserved, I'm sure Einstein wouldn't take too long to throw a spanner in the works in the form of another ingenious thought experiment.